All right, great. Thank you so much. So I'm Jackie. I'm a PhD student at MIT. I'm very excited to share with you this work with my advisor, Vivek Farias. So I don't need to emphasize to this group here that algorithmic fairness is an important problem, and sort of bias arising from algorithmic systems can have a huge impact on society. And so there's a large, vast literature, growing literature in this field of algorithmic fairness. And so the sort of typical setting that this literature studies is sort of the offline machine learning setting. But sort of the offline setting is somewhat constrained in that sort of how well your algorithm or how fair it can be is essentially a function of the training data. And so, one way to kind of bypass this issue of being attached to the data set is essentially to use online learning, where you essentially kind of create your own data set as you go along. And so it is well known that, for example, in a bandit scenario, if you use these exploration-based policy and you get to control the data generating process, you'll eventually converge to the optimal policy. And often optimal is often what you want in fairness. So to give you a concrete example, take the example of algorithmic hiring. So there's actually this very nice paper called Hiring as Exploration, and this is a paper actually in this conference, that show that if you use exploration, you can immensely improve both the diversity and the quality of your hiring rule compared to a kind of offline static machine learning model. And amazingly, they don't even explicitly incorporate fairness into their bandit model, because exploration sort of implicitly tries to give more opportunities to sort of historically disadvantaged groups. So my point here is that exploration can be a useful tool in algorithmic fairness. Obviously, it's not going to solve every algorithmic fairness problem, but it can be used as a useful tool. So in our work, what we study is actually fairness in exploration. So the question that we ask is actually, can the process of exploring be unfair? And of course, I'm going to make precise what I mean by unfair in a minute, but unfortunately, the answer to this question is yes, exploration can be unfair. And this type of bias arising from exploration has not been something that's well studied or well even identified prior to our work. So essentially, kind of a high level idea or message of our work is that naive exploration strategies can lead to unintended disparities. So we have to be very careful in designing our exploration strategies in certain online learning scenarios. So now let's get to sort of the main idea of our work. And I'm going to illustrate this idea through a case study that we did on warfarin dosing. So warfarin is a drug. It is a blood thinner whose optimal dosage varies highly across patients. So we're going to tackle the problem of learning the optimal personalized dosage of warfarin. And we're setting this up as an online learning problem. And so, since this is a short talk, I'm not going to go through the details of the model or the exact simulation setup. So I want to kind of display the main ideas without getting too bogged down in the details. But essentially, we use a warfarin data set, and we create a bandit instance off of this data set. And we simply run a bandit policy. And I'm just going to show you the results from this bandit policy. So in this data set, the patients, we have many covariates on them, and we're going to group the patients into groups. And I'm going to group these patients based on race. And so the results from this bandit, I'm showing you group regret, which is the regret incurred by each group. So there's two groups here, and group regret, you can think of it as sort of the number of mistakes that the policies made on patients of this group. So essentially sort of higher regret means sort of worse outcome for that group because there were more mistakes. And these numbers are normalized to account for like the prevalence of the group. So why is regret even incurred? It's effectively due to exploration. The policy needs to kind of try all different actions and to eventually learn what's the best action. So exploration is what's causing regret. And note that exploration is something that's shared across groups because there's sort of cross-learning across groups. So this is a contextual bandit model where there's cross-learning. So essentially exploring for one group actually benefits another group. And so the question that I'm going to ask is this a fair outcome? More specifically, is each group taking on their fair share of exploration? And so even though group B has much higher regret than group A, I claim that the answer to this question is unclear from looking at these numbers. Because what if it's the case that patients of group B are innately harder to learn than patients of group A? Then it makes sense that group B would have more regret than group A. So for example, when would this occur? Maybe patients of group A are completely homogeneous. They all have the same context. Then it's very easy to learn what we only have to learn one thing, the optimal dose for one type of patient. And so since I didn't really tell you about how the contexts were distributed between the groups, it's unclear whether this is a fair outcome or not. So to address this issue of sort of innate hardness, we want to understand sort of how much cross-learning is there between the groups. And we're going to consider the hypothetical scenario where there's no cross-learning across the groups. So we're going to consider the scenario where each group is on their own and they have to explore on their own. So they can't rely on the other group to do the exploration for them. So we evaluate this hypothetical scenario, and here are the results that we get. So we see that when the groups are on their own, the regrets incurred are 74 and 78 respectively for the two groups. So these numbers are very similar, which means that it's not the case that group B is innately much harder to learn than group A. But when the groups are together, group B ends up taking sort of more of the exploration, and group A benefits a lot from group B, and group B benefits sort of slightly from group A. So so now I want to essentially formally define fairness with respect to this example, and I'm going to do this by plotting these points on a graph. So essentially the two axes represent the two groups, group A and group B, and I'm plotting negative regret. So regret is something that's bad, so negative regret is something that's good. So it's better in this direction. So the purple point is the outcome that we got, which is the negative of the outcome that we got. And the blue point is the hypothetical scenario when groups are on their own. And so let me just redraw the lines of the axis so it looks like this. And the reason why I'm doing this is because I want to treat the blue point as a reference point. And I'm going to measure all outcomes with respect to the blue point. So essentially this red line represents the utility gained by group A. So essentially how much did group A benefit from the presence of group B? And similarly, this vertical line is group B's utility gain. And I'm going to just redefine the origin as the blue point. And this is what we call the disagreement point. So this is the point when the two groups don't sort of cooperate and exploration is not shared between the groups. And now the two axes represent utility gain, and the purple point is now the difference between the two groups. So we're back in the positive orthant again. Okay, so now we're going to define fairness with respect to these utility gains. So we still have this purple point, but whether this is a good outcome or not depends on what other outcomes are feasible. Because if we ran another bandit model or bandit policy, we would essentially get another point in this plot. So that's what we first have to understand. So for example, maybe the set of all feasible outcomes looks like this shaded region. So we'll assume for now that we know what this feasible outcome space looks like. And then we have the question, okay, well, out of these feasible outcomes, what is the sort of the most fair outcome? Is the purple point the most fair outcome? And the way that we're going to define fairness is we're going to go back to foundational economics. We're not going to sort of reinvent the wheel in terms of defining fairness. We're going to use the axiomatic bargaining framework. And so what this is we state a set of axioms that we believe a fair solution should satisfy. So I'm not going to go through these axioms, but for example, Pareto optimality is clearly a desirable property of a fair solution. And we simply define a solution to be fair if it satisfies these axioms. And so these are kind of fundamental axioms from the welfare economics literature. And the seminal work of Nash showed that if you want to satisfy these axioms, there's actually only a unique solution. And it is the solution that maximizes the sum of the logs of the utility gains, or equivalently maximizes the product of the utility gains. And this is what's called the Nash solution, or the proportionally fair solution. So this is how we're going to define fairness with respect to our bandit model. So essentially in the feasible region that we had, that shaded region, the unique fair solution is the point that maximizes the sum of logs of utility gains. Okay, so now we have our fairness definition, and now I'm going to spend the next remaining 5 minutes of this talk going through these, answering these natural questions that arise from our model. So the first question is, how fair are regret optimal policies? And the reason why we ask this question is because the bandit literature is very good at coming up with algorithms that are that minimize regret, right? But so these algorithms, how well do they do in terms of fairness? And so the answer to this question is that regret optimal policies are unfair. And just to give you a high level idea of what I mean by unfair, when you run a regret optimal policy, it turns out that one group ends up incurring the entire burden of exploration. And specifically, this group is the group with the worst best option. So basically their best option is the worst. And so to give you some intuition on why this is the case, essentially this group incurs the least regret from exploration because their other options are also bad, right? So they have a bunch of options, but all of them are bad. So they kind of incur the least regret from exploring. So essentially any algorithm that tries to minimize regret will take the most advantage of this group and try to do exploration on this group because they don't incur that much regret. But they end up incurring all of the regret because it's the most efficient to explore with this group. Okay, so essentially the first question says that we can't use a regret optimal policy. So then the next natural question is, okay, then what is a fair policy? Is there a policy that achieves the Nash solution? And so I won't go into details of how we derive this policy, but essentially the first thing we need to do is that we actually need to characterize this feasible utility set. And so we do this. I won't go into details of how we do this, but essentially we can construct this set, write this set big U, which characterizes exactly this shaded region. And note that big U is a function of theta, which is the unknown bandit parameter. So essentially, we want to find the solution that maximizes the sum of the logs over this utility set. But the first problem we run into if we want to do this is that we don't know theta because theta is the unknown parameter of the bandit problem. So what our policy does is we solve this optimization problem using an empirical estimate of theta at every time step, and we sort of follow this solution. And we essentially prove that this policy, the utilities induced by this policy achieve the Nash solution in this problem, sort of in the asymptotic regime. Okay, so we have a fair policy now. And the last natural question is, how does this policy do in terms of total utility? So do we lose a lot in terms of total efficiency when we use the fair solution compared to a system optimal solution? And so the short answer to this question is that the price of fairness is small. So the price of fairness is defined as the percent of total utility that's lost compared to the outcome that maximizes total utility. So basically a smaller price of fairness is better. So we show one theoretical result, which is a worst case result. And it says that the price of fairness is at most 1 minus 1 over square root of G, where G is the number of groups. So if G is small, which it usually is the number of groups, then this worst case bound is also small. But also we run some simulations where we sort of generate random instances to get a sense of what the average price of fairness is, not just in the worst case. And in our simulations, the price of fairness is always very small. So it's sort of for randomly generated instances. It's usually on the order of 10% or less, even for a large G. So essentially, we believe that sort of we can tighten this theoretical guarantee, and it's not necessarily tight for our set of, for our problem. Okay, so those are the three main questions that are paper answers, and obviously I didn't go into them in detail. But okay, so last thing, I just want to go back to the warfarin example and tell you what happens when we run this fair policy. So this is the point that we had before, which is the regret optimal, and this policy was the regret optimal solution, actually, the regret optimal policy. The fair policy that we get is here. So essentially the utility gain for group B increases, while the utility gain for group A decreases. So the utilities kind of balance out between the groups. And the price of fairness is actually small because the total utilities are actually very similar across these two outcomes. Okay, so I think I'm out of time. Thank you so much for listening. I'm happy to take questions over email or offline. Thanks.